Hello everyone, welcome to my presentation video. My name is Bin Ouyang. I'm currently a postdoc working with Professor Gerben Cedar at the University of California, Berkeley. So today it's my great pleasure to have this opportunity to talk a little bit about how to use entropy as a tool to manipulate the ionic transport through disordered rock-salt ceramic materials. So let me first introduce a little bit about my vision of this field of entropy stabilized materials. So it's it's like a long-standing topic in the field of metal alloys, but I also would like to emphasize that even in the field of functional materials, entropy stabilized materials are very important. Here I give some examples covering fuel cells and batteries and photovoltaic and similar electricities. So you can always see this kind of a solid solution actually outperformed any other kind of ordered version of materials. So that kind of rings a bell, like high entropy may not only be important for metal alloys, but also going to be important for functional ceramic materials. So today, let me give example of this disordered rock salt materials. And here I'm looking at two materials as a solid solution. Well, the first one is lithium manganese titanium oxide. The second one is lithium manganese zirconium oxide. So if you're working in the field of lithium-ion battery, you maybe agree with my point that like these materials are quite similar. Like they have the same amount of lithium, which is a carrier of the energy, and they have the same amount of manganese, which is the active metal, which is also like the redox metal. So the only difference is here is the titanium and zirconium, but they are not so important because they are inert metals. They doesn't get involved into this chemical reaction. So you're gonna expect the performance of these two materials to be at least similar, right? But if you make them into batteries, you're gonna realize they are not even similar. Like the first material, the zirconium version, only have half of the capacity with the second materials, which is the titanium version. And if you do collateralization on this, XRD gonna tell you nothing because they have exactly the same crystal structure, even with the small differences on the lattice constant. But if you do something like electron diffraction, that actually tells you something. They have exactly the same amount of Bragg peaks, which is a long-range ordering, but they also have very different diffusive scattering patterns. And those patterns are actually called chemical short-range order. So the definition of the chemical short-range order exists widely in all kinds of solid solutions. Like for instance, in this disordered rock salt lattices, we have oxygen sublattice and also the cation sublattices. So the cation sublattices can be partially occupied. So that's a sign of disorder, right? So which means the distribution of these cations are random. But something doesn't have to be random. The pulse doesn't have to be random. And we can actually quantify this randomness by using this Warren-Cauchy short-range order parameter. It can be calculated as 1 minus the ratio of finding B parting with A divided by the concentration of B. So if this is 0, it's free random. And if there is a short-range order, you're going to get a non-zero short-range order parameter. So if you take a Fourier transformation of this short-range order parameter, you're going to get exactly the analytic form of this diffusive scattering pattern because that it can be derived from the Patterson function. So that is the physics basis of short-range order. And we actually developed a computational suite to capture this short-range order, which usually starting from the density functional theory calculations on a variety of different orderings and energetics. And on base of that, we can fit that into a Hamiltonian called the classic expansion. So we get a map between the energetic space with the configurational space. And on top of that, we can do more realistic simulations by using, Monte Carlo sampling. And in that case, we can get a finite temperature configurations that can be used to approximate with what we see in experiment. And with this kind of a modeling suite, now we can model the short-range order pattern that we see in experiment. In the first one, we see a ring, so we can reproduce the ring. And in the second one, we see a 4-point contrast maximum, which can also be reproduced by our computational suite. So now we have additional tools on top of electron diffraction, right? Because by using these computational tools, we now can have a realistic atomic model. And with this kind of a model, now we can understand a little bit better on what exactly happens. So what exactly happens to this battery is that in this kind of a structure, we may have this local structure called 0Tm unit. So it's a tetrahedron with 4 lithium occupied by all the sides. So in other words, the lithium is going to diffuse much faster in this 0Tm unit compared with other units, which, according to some of our earlier work. So what do we need to do? Naturally, going to be maximize the amount of 0Tm unit and make sure they are well connected with each other, right? So in that case, we can form this kind of a highway for lithium transport. So that is actually the reason why these materials work. So, and then we can combine our simulation to, explain what will happen in experiment. So in these two materials, we see these different diffuse scattering patterns, right? So we can simulate this pattern and get atomic configurations. And then we can draw this percolation network of these materials. And the percolation network actually rings a bell. The reason why the first materials only have a half capacity is because they have much less of this coverage of lithium transport highway. So that's going to be the reason for the performance. With the understanding of that, now we can rationalize a little bit, right? So we can design this kind of a percolation map as a function of a composition in this kind of a quasi-high entropy system. So we have 4 cation species and 2 anion species. And using this map, first of all, we know how to maximize our capacity, right? At least the initial capacity. If you go from 4 to 1, you are essentially maximize the extractable amount of lithium. And that is confirmed by my experimental collaborator. And on the other hand, if you want to chase for something else, for instance, like retention, then you can go from the right hand side to the left hand side, right? Because as shown by these contour lines, the left top hand side is going to have the largest electron capacities, and that is a sign of less oxygen evolution. So it means better retention. So that is also confirmed, if you compare compound 2 with compound 5, compound 2 actually, even though starting with a high capacity, but they're going to have a terrible retention performance, while compound 5 is reasonably good. So with this kind of a map, now we can rationalize our composition optimization a little bit, right? So without even doing experiment, we already know this is going to be the sweet zone, which is the red shaded region. So now we can scale it up a little bit by examining multiple systems, for instance, nickel and manganese-based system. And the reason for that is, these 2 elements are inexpensive. So we can make, inexpensive lithium battery on top of it. So here I plot the percolation map of these 4 systems, and also with this kind of a shaded region showing this is not accessible by experiment. And if you take a second look at this map, you're going to realize something similar, right? So you can always draw this kind of a curvature. And if you zoom in the curvature by drawing this kind of a line at fixed lithium content, you're going to realize, they have the same behavior. The first behavior is that you can always hit a minimum of capacity when you have a small amount of fluorination. So that kind of rings the bell, if you want to dope these materials, it's not really a good idea, like a small amount of doping can actually decrease and also have some detrimental effect to the 0Tm percolation. And this is not the most important information. Well, the most important information is actually the dashed lines. So the dashed line is the state when we have also random of the power distribution. In other words, the short-range order parameter is 0 at this dashed line. So this is actually a reasonably good state, right? So which make us think about, how to make a free random alloys to achieve free random in those materials. So there are good news and bad news here. So the bad news here is that it's almost impossible for those materials to be fully random. It's very challenging by using our typical synthesis method. And the good message here is like we have the tool to go high entropy. So I actually learned this from the community of metal alloys. Like we call high entropy materials multi-principal component materials. That also rings a bell. We can dilute those dominated short-range order interactions in the materials by going high entropy, right? So that's going to effectively reduce the short-range order features in these materials. So with this kind of idea, I first did a high throughput computation for about 8,000 of high entropy disorder rocksalt materials. And I can plot this distribution of this randomization temperature, which I call the mixing temperatures. So it's kind of obvious that high entropy DRX generally going to have a lower random temperature compared with the low entropy DRX. So that is a good sign. On top of that, we also realize, it's not so chemistry dependent if you go high entropy, as in low entropy, there are some elements which doesn't really like disorder rocksalt lattices. But if you go high entropy, most of the elements looks green. So in other words, they are relatively compatible to this disorder rocksalt lattice. So on basis of these two good signs, the next thing we want to do is to propose, like a promising composition, right? So we came up with this kind of a compatibility map idea. So it's an interactive heat map of the compatibility of different metal species. So you can go to the link I provided to play with this map. And the messages we can have here is, like some metals prefer to mix with other metals, but some metals are not. So when we design a high entropy composition, we can take references of this kind of computational data to find a good and also a promising composition. So let me give an example here. So we have a pool of 7,965 high entropy cathode materials. And among them, we have found these two materials which are going to have reasonable randomization temperature, and also, they're going to have reasonable Serratic capacities. And my experimental collaborators actually made these materials and first did an electron diffraction on those materials. And we sort of realized, like these materials, if you have only two transition metals, they have significant short-range order features, which I'm pretty sure you can see with your bare eyes. But if you go to full transition metal, it gets weaker, but you can barely see it. And if you go to 6 transition metal, they almost disappear. So that actually proves our hypothesis that high entropy is going to get rid of this short-range order. On top of that, we then, measure the performance of these materials, because according to the percolation theory, they're going to have a better performance, right? And it's also confirmed, 2 transition metal only have 220 milliampere-hour per gram of capacity, but if you go to high entropy, they can reach 307 milliampere-hour per gram. And maybe you're going to argue a little bit, this is not essentially necessarily related with kinetics, right? Because zero-TM percolation is essentially a kinetic factor. There are so many other reasons for the performance. So what we need to do next is to verify this is indeed kinetics, right? Electrochemical test we can do is for this rate test. So we can cycle this battery at different rates. So if you have a bad kinetics, for instance, like the 2 transition metal materials, you're gonna see a significant fading of these capacities. Like at 2 ampere-hour per gram, you can only have 50 milliampere-hour per gram of battery capacity. But if you go to 6 transition metal, you can still maintain about 180 milliampere-hour per gram of capacity. And that is comparable with the commercialized battery in our state-of-the-art electric vehicle. So that is also a good sign, like by making these high entropy battery materials, you can reach the full capacity of the NCA cathode materials if you are driving a Tesla car in about 10 minutes. So that is a good sign for using these high entropy materials. And that is pretty much of my presentation. I really would like to thank those experts from different fields, and thanks for the collaboration and insight to all the work I presented. And also I'd like to thank the funding from both the DOE and the UMICO, which is our industry partners. And that's pretty much about my presentations. I really appreciate your attention, and please feel free to reach me if you have any questions.